What if the most advanced civilizations in the universe aren't hiding but glowing? For decades, we've scanned the cosmos for radio signals and heard nothing but silence. But silence doesn't mean emptiness. It may mean we've been listening for the wrong kind of evidence. A Dyson sphere is a hypothetical megastructure built to capture the energy of an entire star. And while a civilization might hide its light, it cannot escape the second law of thermodynamics. Energy can't be destroyed, only transformed into waste heat. If such structures exist, they wouldn't look like stars. They would appear dark, invisible light, yet burn brightly in the infrared. So the real question isn't where they are, but if physics demands they glow, why do our telescopes see only darkness? If we follow the infrared signal back to its source, the search becomes a game of statistical elimination. We are not looking for radio messages or interstellar monuments. We are looking for stars that are leaking the wrong kind of light. This is the exact methodology behind Project Hephaistos. In a massive forensic sweep of astronomical data from the Gaia and WISE observatories, researchers analyzed the spectral signatures of over 5 million stars. Their objective was to find outliers, objects that violated the standard models of stellar physics. After filtering out the noise of young stars and dusty nebulas, the algorithm narrowed the list down to just 7 candidates. These 7 objects, all M-dwarf stars, present a compelling anomaly. They are dimmer than expected in the visible spectrum, but they exhibit a distinct infrared excess. To an optical telescope, the star appears to be fading, obscured by some intervening material. But to an infrared sensor, the system is blazing with thermal emission. In observational terms, this is a strong diagnostic signature consistent with a significant fraction of starlight being intercepted, absorbed, and re-radiated as waste heat. However, finding an anomaly is not the same as finding a civilization. It is the observational equivalent of feeling the heat from a car engine hood in a pitch-black garage. You cannot see the machine, but the thermal trace confirms that work is being done. However, finding an anomaly is not the same as finding a civilization. Before we can claim these 7 candidates are technological in nature, we must subject the very idea of the Dyson Sphere to a rigorous energy audit. We must apply rule number 0 of this investigation. Heat is evidence of work, not intent. We do not assume that an advanced civilization builds a Dyson sphere for aesthetic reasons or to signal their presence to the universe. We assume they build it because their energy demands exceed planetary limits. A civilization is fundamentally a complex heat engine. It consumes low-entropy energy such as starlight to maintain its structure and information, and it excretes high-entropy waste heat. As a technological society expands its energy, appetite grows exponentially. The physicist Freeman Dyson calculated that even at a modest growth rate of 1% per year, humanity would require the total energy output of the sun in just 3,000 years. Under continued technological growth, this is less a choice than a thermodynamic constraint. Eventually, the surface of a planet or even the total nuclear fuel available on a planet becomes insufficient. The only remaining reservoir of energy in a solar system is the star itself. Therefore, the Dyson Sphere is not a sci-fi fantasy. It is the logical endpoint of any civilization that survives long enough to outgrow its planet. It is an industrial solution to an energy crisis. But if we are to understand how such a solution is engineered, we must first dismantle the popular image of what this structure actually looks like. The vision of a solid shell enclosing a star is not just a myth, it is a physical impossibility that would collapse before it was ever finished. To understand why, we need to look at what gravity actually allows and what it does not. The image of the Dyson Sphere, a solid monolithic shell completely enclosing a star, is arguably one of the most persistent misunderstandings in the history of science fiction. It is a structure that exists almost exclusively in the realm of television and cinema, most notably popularized by Star Trek: The Next Generation, where the crew of the Enterprise encounters a continuous metallic surface with a diameter of 200 million kilometers. However, this was never what Freeman Dyson intended. To understand the true nature of the concept, we must return to its original formulation. The concept did not originate in a physics lab, but in the 1937 novel Star Maker by Olaf Stapledon, which described a gauzy web of light surrounding a star. Inspired by this vision, Dyson published his seminal paper in the journal Science in 1960. He used the term artificial biosphere to describe a loose collection of habitats and energy collectors. He explicitly noted that a solid shell would be mechanically impossible. Yet the public imagination latched onto the idea of the solid sphere, ignoring the chaotic reality of the swarm. The difference is structural and functional. A solid sphere is like a balloon, a single continuous membrane under immense tension. If one part fails, the entire structural integrity is compromised. A Dyson swarm, by contrast, is better understood as a dense orbital cloud of independent structures. It consists of quadrillions of independent satellite solar collectors and habitats, each orbiting the star in a dense coordinated formation. The swarm model solves the problem of rigidity, but it introduces a problem of complexity. Instead of building one massive roof, a civilization must manage the orbital trajectories of 10 to the power of 15 independent objects. But why is the solid shell impossible? Why can't a sufficiently advanced civilization simply synthesize a material strong enough to build a roof over their sun? The answer lies not in the limitations of technology, but in the fundamental laws of gravity itself. If you were to build a solid sphere around a star, you would immediately run into a gravitational result known as the shell theorem, which can also be derived from Gauss's law for gravity. Intuitively, one might assume that the star's gravity would pull the sphere inward equally from all sides, keeping it perfectly centered. The math, however, proves the exact opposite. Inside a spherical shell of uniform mass, the gravitational force exerted by the shell on any object within it cancels out to zero. More critically, the net gravitational force exerted by the star on the shell is also zero. This creates a state known as neutral equilibrium. The shell is not held in place, it is drifting. There is no restoring force to keep the star centered. If a stray asteroid nudges the shell, or if the star wobbles slightly, the sphere will begin to drift. Since there is no gravity to pull it back, the movement continues unchecked until the side of the sphere crashes into the surface of the star. Without active propulsion systems firing constantly to correct its position, a waste of energy that defeats the purpose of the structure, a solid Dyson sphere is essentially a slow-motion collision waiting to happen. Even if we could magically keep the star centered, the sheer mechanical stress on the structure would be fatal. A rigid shell at a distance of 1 astronomical unit, the distance from Earth to the Sun, would not simply remain in place. It would be subjected to the star's gravity, crushing it inward through compressive stress, while the centrifugal force of its own rotation would pull it apart through tensile stress. Because a sphere behaves like a bridge arch, every section depends on its neighbors for support. The resulting pressure on the material would be extreme. To prevent the shell from buckling under its own weight, the construction material would require an elastic modulus of approximately 10 to the power of 13 gigapascals. To put this scale into perspective, the strongest chemical bonds in nature, found in diamond and graphene, produce materials with a strength of roughly 1,000 gigapascals. This means a solid Dyson sphere requires a material 10 billion times stronger than diamond. No atomic bond known to standard physics can provide this strength. The bonds would simply snap and the structure would crumple like aluminum foil. Therefore, the solid shell is a structurally non-viable system. It is a fundamentally unstable gravitational configuration. If a civilization wants to harvest their star, they have only one option. They must shatter the shell into billions of free-floating satellites. But this leads to a new, equally brutal industrial challenge. To build a swarm of that magnitude requires a quantity of raw material that simply does not exist on the surface of any habitable world. The scale of the swarm transforms construction into a planetary-scale industrial problem. To build the machine, they cannot just mine a planet. They have to unbind it. If the solid shell is a myth and the swarm is the reality, we face an immediate logistical crisis. Where do you find enough matter to build trillions of orbital structures? A Type 2 civilization cannot simply launch material from their home planet. The cost of overcoming gravity to lift that much mass would be prohibitive, and dismantling their own biosphere would be ecologically catastrophic. They need a dead world, a reservoir of raw materials that can be sacrificed for the greater good. In our solar system, the prime candidate for this planetary unbinding is not the asteroid belt, which holds surprisingly little mass, nor the gas giants, which are composed mostly of useless hydrogen and helium. The ideal feedstock is Mercury. Mercury is the most efficient candidate for a mega engineering project. Its interior is dominated by a metallic core that accounts for roughly 85% of its radius. It has no atmosphere to create drag for launch systems, and its surface gravity is less than half of Earth's. Most importantly, it sits deep within the sun's gravity, well bathed in an intensity of solar energy almost 7 times greater than what we receive on Earth. The dismantling of Mercury would not be an explosion. It would be a controlled, methodical deconstruction, the cosmic equivalent of taking down a skyscraper brick by brick to pave a road. It begins with a seed, a single automated base landing on the planet's surface. This base deploys solar collectors to power mining crawlers. These crawlers strip mine the surface, processing the regolith into refined iron and silicates. But instead of building cities, they build mass drivers, immense electromagnetic railguns stretching across the cratered landscape. These railguns are the arteries of the construction project. They fire packets of refined material, glittering solar sails, or folded satellite components into orbit at escape velocity. As the project scales, the planet does not just get mined, it gets consumed. The crust is peeled away, then the mantle, and finally the iron core. Over centuries, Mercury's mass distribution is progressively dismantled. It is converted into a diffuse cloud of intelligent machinery, spread thin to intercept the starlight that once scorched its surface. But physically removing a planet from existence requires overcoming one of the most stubborn barriers in astrophysics, the energy bill. Gravity is a binding contract. To take a planet apart, you must pay its gravitational binding energy, U. This is the total energy required to separate every atom of the planet and move them to infinity, effectively the energy needed to overcome the planet's own gravity, holding it together. For a dense rocky world like Mercury or an Earth-sized planet, the formula U equals 3gm squared divided by 5r yields, a staggering cost. To unbind a planet the size of Earth, you need approximately 2 times 10 to the power of 32 joules. To unbind a gas giant like Jupiter, the cost jumps to 2 times 10 to the power of 37 joules. To put that order of magnitude into perspective, 10 to the power of 37 joules is roughly equal to the total energy output of our Sun for 800 to 1,000 years. This means that even if we covered the entire Earth in solar panels and saved every watt for a millennium, we would still not have enough energy to disassemble Jupiter. It seems like a paradox. You need a Dyson Sphere to get the energy to build a Dyson Sphere. The solution lies in the economic principle of bootstrapping, or more precisely, the feedback loop. The construction does not happen all at once. The first wave of satellites launched from Mercury might capture only 0.0000001% of the Sun's energy. But that tiny fraction is still immense compared to planetary power plants. This energy is beamed back to the surface of Mercury through lasers or microwaves to power the next generation of railguns and mining crawlers. This creates a positive feedback loop. More satellites mean more energy. More energy means faster mining and more powerful railguns. More railguns mean more satellites launched per day. This is the power of compound interest applied to astrophysics. What starts as a slow, localized mining operation eventually accelerates into a geometric explosion of productivity. Within a few centuries, the energy available to the dismantlers exceeds the binding energy of the planet itself. The star's energy output is progressively redirected to power the construction process. However, energy is only half the equation. The other half is time. If humans were to manually build these satellites, the project would take geological eras. To finish a Dyson swarm within a civilization's lifespan, we need a workforce that grows as fast as the energy supply. No biological species has the patience or the numbers to screw together a quadrillion bolts. The only workforce capable of building a Dyson swarm is a workforce that builds itself von Neumann probes. Named after the mathematician John von Neumann. These are self-replicating spacecraft. The logic of the multiplication engine is simple. Probe A lands on an asteroid or planet. It mines raw materials to build a copy of itself, designated as Probe B. Probe A and Probe B then work together to build probes C and D. This is exponential growth 2, 4, 8, 16, and so on. If a probe can replicate itself once every year, then after just 30 years, you would have over 1 billion probes. In theory, unchecked exponential replication quickly runs into physical and resource limits. In the context of a Dyson swarm, these probes serve as the construction workers. They are not distinct from the swarm, they are the swarm. The mining crawlers on Mercury are von Neumann machines. The railguns are self-expanding infrastructure. However, real-world engineering imposes strict limits on this mathematical dream. The primary bottleneck is not reproduction speed, but production yield and defect rates. Industrial replication is never perfect. If a parent probe has a 0.1% mutation in its blueprint code, and that error is copied to the child probe, the error propagates. Over 1 billion generations, the swarm could evolve into a runaway non-functional replication cascade satellites that consume resources but fail to deploy their solar sails or railguns that fire off target. Therefore, a Dyson swarm requires a centralized verification and control system, a master control system that verifies the integrity of every copy. This prevents the multiplication engine from becoming a mutation engine. But assuming the replication holds steady and the planet is successfully converted into 1 trillion autonomous satellites, the civilization faces a final, terrifying logistical hurdle. They have successfully filled the sky with machines. Now they have to make sure those machines don't destroy each other. We tend to visualize a Dyson swarm as a graceful, orderly shell. In reality, it would look more like a cloud of angry gnats. A mature Dyson swarm consists of perhaps 10 to the power of 15 distinct individual objects, roughly 1 quadrillion. Each one is moving at orbital velocities of tens of thousands of kilometers per hour. Unlike cars on a highway, orbital objects do not have brakes. They are governed solely by their velocity vectors and the gravity of the star. If 2 of these satellites collide, they don't just dent, they pulverize. The impact energy vaporizes metal and shatters solar panels into thousands of pieces of shrapnel. Each piece of shrapnel becomes a bullet, creating a new orbit that intersects with other satellites. This is the Kessler syndrome taken to a stellar extreme. A single collision could trigger a cascading chain reaction that shreds the entire swarm, turning the megastructure into a mega cloud of abrasive dust and debris. This dust would then form a shroud around the star, blocking the light for the remaining collectors and potentially rendering the solar system unusable for thousands of years. To prevent this catastrophe, the swarm requires an active orbital traffic control system of incomprehensible complexity. This system cannot rely on passive orbits. The satellites must be statites, meaning static satellites. They use the pressure of sunlight acting on giant solar sails to hover against gravity, or they arrange themselves into distinct, non-intersecting rings. The computational power required to calculate and adjust the trajectories of 1 quadrillion objects in real time is immense. It suggests that a Dyson swarm is not just a power plant, it is also a supercomputer. The sheer density of the swarm means that the space around the star becomes a high-velocity fluid of metal and silicon. It is a system teetering on the edge of chaos, maintained only by constant orbital corrections. So if a civilization manages to unbind a planet, pay the energy bill, replicate the workforce, and prevent the traffic from crashing, they win. They achieve the status of Kardashev Type 0 and 2. They have access to essentially infinite energy. But physics is a transaction. You get the energy, but you must pay the tax. And the tax is heat. If a civilization succeeds in this monumental engineering feat, they do not just change their energy supply, they fundamentally alter the thermodynamics of their solar system. This brings us back to the central premise of our forensic audit: energy cannot be destroyed, only degraded. Every watt of starlight captured by the Dyson swarm performs work powering a supercomputer, driving a laser propulsion system, or lighting a habitat. But once that work is done, the energy degrades into low-grade waste heat. This is not a technological flaw, it is the second law of thermodynamics. No physical process can operate without dissipating energy. For a Dyson sphere, the exhaust is infrared radiation. If the swarm were to capture 100% of the star's energy and refuse to release it, the interior temperature would skyrocket. The internal equilibrium temperature would rise catastrophically. Within days, the delicate machinery of the satellites would melt. Within weeks, they would vaporize. To maintain structural integrity, the system must continuously radiate waste heat into space. The builders must radiate that heat out into the void. A Dyson swarm designed for habitation or computing would likely operate at a room temperature of roughly 300 Kelvin. According to Wien's displacement law, an object at this temperature radiates most strongly in the mid-infrared part of the spectrum, specifically peaking at a wavelength of roughly 10 microns. This creates the specific fingerprint we are hunting. To a distant observer, the star has vanished, replaced by a giant glowing coal. But the consequences go deeper than just heat. The structure also affects the star itself. In a dense swarm, a fraction of the collected light is inevitably reflected back onto the stellar surface. This photonic feedback adds extra energy to the star's photosphere. The star responds the way any gas ball does. When heated, it expands. This phenomenon, known as stellar puffing, causes the star's radius to swell and its core pressure to drop. Paradoxically, this slows down the nuclear fusion rate. By effectively wrapping the star in a thermal blanket, the civilization extends the star's lifespan, whether inadvertently or intentionally. They are not just harvesting the star, they are coupling its evolution to an engineered system. The star and the machine become a single, symbiotic thermodynamic entity. So we have the profile of our suspect, a dark object radiating at 10 microns, influencing the physics of its parent star. With this profile in hand, we return to the evidence locker. We return to Project Hephaistos and the 7 M-dwarf stars that made the final cut. Why M-dwarfs? These red dwarfs are the longest-lived stars in the universe, capable of burning for trillions of years. If a civilization is building a megastructure, they are investing in the long game. They wouldn't build a monument around a volatile, massive star that will go supernova in a few million years. They would build it around a long-lived, low-mass star like an M-dwarf. The 7 candidates identified exhibit the classic infrared excess we predicted. They are faint, invisible light, but bright in the infrared. However, in forensic science, a match is not a verdict. We must rule out the false positives. The universe is dusty. When asteroids collide, or when planets form, they create massive debris disks, rings of rock and dust that absorb starlight and re-radiate it as heat. To a telescope looking from hundreds of light years away, a natural ring of dust and an artificial swarm of satellites look frustratingly similar. They both block light. They both emit heat. The difference lies in the spectral shape. A natural dust cloud is messy. It contains grains of different sizes and temperatures, creating a fuzzy thermal signature. An artificial swarm engineered from uniform materials and kept at a controlled temperature should look like a black body, a theoretical object with a precise, sharp thermal curve. The 7 Hephaistos candidates are outliers because their signatures are difficult to explain with simple dust models without invoking extreme coincidences. But difficult to explain is not aliens. It is simply a mandate to look closer. The next step involves the James Webb Space Telescope. Its sensitivity in the mid-infrared is high enough to distinguish between the chaotic noise of a dust cloud and the rigid order of a megastructure. Until that data arrives, we remain in a state of open case. We have not found definitive evidence of extraterrestrial technology, but we have found the limits of our own understanding. Whether these anomalies turn out to be the exhaust of a Type 2 civilization or simply a new violent phase of planetary evolution, the result is equally profound. We are scanning the dark, listening to the thermal whispers of the cosmos. And for the first time in history, we know exactly what we are looking for. We are not searching for messages or monuments. We are testing the limits imposed by physics itself.